Section 8.1 is on arc length. The idea here is we're going to use calculus to, given some function, to find the length of the arc that the function makes, or the length of the curve. So here's the idea behind it. In a lot of the other things we've done in this class, the idea was start off with a bad approximation and then make it better, either by using more rectangles, or in the case of those volumes we did, using more slices, more thinner slices. Here what we're going to do is we're going to approximate this by looking at line segments. So like if you put one line segment from one end to the other, that would be a pretty awful approximation of the length. But if we cut this into two pieces, and we did this segment plus this segment, that would be a better approximation. And the more dots we put in there and the more segments, the better the approximation will be. So what I'm going to do is, at each one of these, I've got the little tick marks there with the dots. I'm going to put in a dot here at 1, here at 2, 3, 4, 5, 6, and 7. And that's going to allow me to draw in, I guess, 6 segments. Let me try that one again. I've got 6 segments here. And if we were to take the length of those 6 segments and add them up, then that would be a better approximation. And of course, the more segments we put in, the better it'll be. So the idea here is that we're going to use the distance formula or the Pythagorean theorem to come up with the lengths of these things. Well, let's pick one of these. I'm going to pick this one, and I'm going to call this point x1, y1, and this point x2, y2. And I'm going to draw in a right triangle here. The drawing's not perfect. Let's pretend that's a right triangle. All right. I'm going to call my 3 sides. I'm going to call this one A, this one B, and this one over here I'm going to call capital D. So if you look at this from the, you get capital D, let me change to a thicker line. You get capital D squared is A squared plus B squared. And if you want to figure out what A and B are, A is the difference in the 2 y coordinates. So y2 minus y1. And B is the difference in the x coordinates. Now, of course, it doesn't matter if the direction you do the subtraction in, because when you square it, it makes that positive. All right, so what we could do, if we wanted to just do an approximation, is we could use this and approximate each one of these lengths and add them all up. But let's don't worry with doing that. Let's actually approximate it using infinitely many segments. Excuse me. So here's the plan. Use n segments to approximate the curve length. And then take the limit as n goes to infinity. All right, so when we do that, what we're going to have in our function, there's a bad approximation of the thing I have above. When we do that, let's look at 2 segments here, this little triangle that's really close together. If we take that and blow it up, then we get a little triangle here. Now, this is a tiny change in y. This is a tiny change in x. And this up here, we call it a tiny change in s. S is what's used here for like the curve, or ds is always used for a tiny change along the curve. And so if you take this and put it together, you get ds is equal to, well, you could say ds squared is dx plus dy, both of those things squared, or ds is equal to square root of 1, or of dx squared plus dy squared. And that ds, again, is just a tiny change along the curve. So here's what we'll do. Once we've got that, I'm going to take this and I'm going to multiply it by dx over dx. So it's dx over dx. And I'm going to move this one inside. The radical. Now, what do I mean? I'm only moving the lower one inside the radical. So when I do that, I get ds is equal to, I'm going to come over here to do this because I might need all that space. ds is equal to the square root of, now when you move it inside, you get, let's see, I've still got the dx squared plus dy squared. But now we've moved the dx inside. And so, of course, you move it inside the radical, you have to square it. And there's still the one left on the outside. So if you take that and you move it inside, or not move it inside, but if you take this and then you distribute it across here, you get dx over dx squared plus dy over dx squared times dx on the outside. And this is just 1. And if you put this together, it gives you what I've got down here in the next block. It says memorize this. ds is the square root of 1 plus dy over dx squared times dx. And what that is, it's a formula for a tiny change along the arc. And the arc length of a curve from A to B is this. You just integrate ds from A to B, and that gives you the length. We'll do some examples of this in the next video.